Okay, we're live. Okay, so this I just want to continue where we left off the last time. So we have the PWM working, we play music, stuff like that. So right now what I want to do is just try out the interrupts and basically take this little couple of those commands that handle the LED flashing and move it into the interrupt routine. So we are going to be using the example that the crate authors kindly provided us with. So this should be quick actually. We are just going to copy the global mutex variables. We are going to adjust the LED to what we are using in here. We could just define the type the way they have it in here, but I wanted to have I wanted to be a little bit explicit, at least for the time being. Yeah, we need to define those first. So we will need the GPO C PC13 and we need output. We will need, yeah, the push pull is fine. Okay, we also need the mutex, and this mutex comes from the Cortex M crate, not from the standard library, because we don't have one in here. And we need the not ref cell, it's just cell ref cell. We won't be needing this, and we won't be needing this anymore, I don't think. So we are talking about PC13 configured as output push pull, and we need counter timer, and we're using the timer 2 for the PWM, so the next one. We will also need the timer object, and the timer, which is pack. So since we're using pack, we need self, and we need the timer 3. So we won't be needing this because that's going to be handled by the interrupt routine, but we do need to define the timer. So timer 1 and timer sorry, no, we're using 3. We're using 3. No, we need device peripheral. Timer 3, we need clocks, and we need the mutable RCC APB2 array. It's APB2 or 1. There, that's assignment. and we need to start the timer. It's start countdown, and we want the same in here. We want 1 second. We want the LED to flash every 1 second. And we start listening on the event, but we need to use it first. And there's only one event defined, which is update. So that essentially configures enables the interrupt on the timer tree peripheral. So now we need to initialize the global mutex variables with our objects. So the LED, yeah, this essentially means Cortex M interrupt free. This essentially means that the interrupts are shut down for the duration of this operation. So basically, while we're doing this, no other interrupt is able to fire and disturb these instructions being executed right now. And we need to do the same for the timer. There. But we name this differently. It's timer 3. There. So we have that. Now we can specify the interrupt routine. So basically, interrupt service routine is just a function named appropriately for the interrupt, and the way or basically if you want to find the name of the handling routine that you're going to use to override the default ones, you can check the documentation and you can find those names in the packed interrupt enum. So each of the elements of the enum is an interrupt routine that you can use, but you need to annotate it correctly. And that interrupt comes from the pack as well. And then within the interrupt, and again, this is not a LED pin. Maybe it was a good idea to alias it after all. And this is timer 3. And we need to mark it as unsafe. And because we were over eager here, we need to disable that. So basically what is happening is that we are moving our resources from our main routine or our main function into the service routine. So we are configuring those static mutable variables that are going to be local to the interrupt service routine, and we're going to move our peripherals into those variables. And that's going to happen during the first execution of the interrupt service routine. So here what's going on is that this get or inset method on the option object, it's going to try to, if that option is some, it's going to take that object out, but if it's none, as it is initially, it's going to execute whenever is provided here within the closure. So that what is going to happen is that we are going to take the object out of our global mutex, replace it with none, and then return that object into our LED. And the same for the timer peripheral. So we're essentially swapping the values of those variables the first time the interrupt is going to fire. And then why would you need a timer in here? Well, LED is obvious because you want to toggle it, but the timer is required in here so that you can essentially clear the interrupt after it fires. Because if your timer is going to fire the interrupt routine is going to be called, and it finishes its execution, no other interrupt is going to be fired ever again. You have to manually clear it by waiting for the timer. So I guess this is it, and we can test. Oh no, actually we forgot about probably the most important part of that. Well, equally important as all the other parts. Basically what we're doing in here we're just enabling the interrupt for the peripheral. But what we still need to do is to enable the interrupt globally for the timer peripheral. And in order to do that, you need to use something called NVIC. And NVIC is the nested vector interrupt controller. It's basically a system that manages all of the interrupts on the device. And that operation is unsafe. And NVIC resides in the pack module, and you don't enable it because I think that's deprecated at this stage. You unmask it, and what you're unmasking is you need to specify exactly which interrupt you're unmasking. Which in our case is timer 3. So once this is configured, here we are actually enabling the interrupts for the entire timers in here in our controller, and basically from this moment on the interrupts should be live. So I guess let's just test it. Okay, it compiles cleanly. We connect it. We run the debugger. So before I started, what we should expect essentially is our melody still playing. Let me just hook it up. So we should be able to hear the music, and we also should be able to see the LED flashing. There. Now we have the interrupt working, which worked quite quickly, to be honest. So I just wanted to have a quick look at what we've done before with the PWM stuff and see if we can maybe make this a little bit more generic. Because in here we actually very tightly coupled to the STM32 F1XX crate, and basically the philosophy behind the embedded hall is that supposed to be writing drivers based on the traits provided by that crate, and those should work with any other crate that also utilizes those traits. So let's see if we can make this a little bit more generic. So instead of using the PWM from this crate, let's use the actual embedded whole PWM trait. So we get rid of this then, and this, and like this. And so let's specify the bounds. Okay, and this is going to be difficult, I guess. So where P is PWM, and so let's have a look at the embedded whole. So we're not gonna look at, yeah, let's look at this one. So how is PWM defined? So channel time and duty. So let's specify where channel is our channel. Time is hertz, which we need to import. And the duty is, I guess, U32. And then this becomes just this. Mismatch. Expect, oh yes, yes, because it's U16. Yes. There. And then all of those imports, they kind of become unneeded. So I guess the last think that we could do, because in here we have the knowledge of the channel 1. So let's just make the channel 1 of the parameters. And then we will specify the channel in our new function. Like this. And then let's just select the channel. There. So then that means that we need to specify the channel whenever we're creating this object. And we're done. Boom. Let's just validate that it's working correctly. And it is. So playing and flashing. So I guess, yeah, we're plowing on. We're unstoppable. In our embedded development.